Okay, I think.
This meeting is being recorded.
So, Joseph, please, whenever you want, floor is yours.
Okay, thank you very much. Thank you for the invitation. Okay, so this is based on ongoing work with my supervisors, Philip and Xenia, and another student, Puru, who's recently taken up his postdoc position. So the objects of interest are Calabi-Yau threefolds, and there's a lot that could be said about these. And what I'd like to advocate today is the viewpoint where you can consider these as varieties over finite fields. So really we're used to considering these as complex varieties or as real manifolds. Okay. Now, when you do this, there's a natural object to sort of study, and that is the zeta function. And I'll explain in more detail what that is, but right now I'd like to just sort of give a general overview of what I want to say today. So there are special cases, which I will explain, where one can look at the zeta function and read off some modular forms. And this is sort of a topic of large interest in Calabi-Yau geometry. It's known that this always happens in this 2009 result for rigid Calabi-Yau manifolds, but it's ongoing studying what happens in manifolds with more complex structure parameters. Now, in 2020, it was conjectured by Caccianelli and Yang that actually supersymmetric flux vacua gave you such special cases. And in that study, they looked at this mirror octic manifold, which had been looked at by Kadir in 2004, and were able to evidence this conjecture. So what I want to really show you is that we've worked out a means of more quickly computing the zeta function for a larger number of examples. And we've tested this in a few cases, and we find agreement with this conjecture. Okay, so let's say that we have your Calabi-Yau over a I hope you can hear me still.
Yes, don't worry.
Okay, thank you. Let's say that we have your Calabi-Yau with rational or moduli that belong to some number field. And if you now look at this over a finite field, then you'll find that it consists of some finite number of points. The finite field depends on the data of some prime. So if you now fix a prime p, and collect all the point counts over the finite fields fp to the n, you can put them into this function, the zeta function. Now, what's sort of amazing is that there are conjectures due to V that this zeta function actually, as a function of t, takes on this rational form. So the denominator is the less interesting part. It's sort of it doesn't change as you vary the complex structure moduli, but the numerator does vary. Sorry, and the degree of the numerator is the third Betti number. And it could well happen that for some values of the moduli, that numerator factorizes and picks up a degree 2 factor. And when this can happen, this number alpha will be the coefficient of q to the p in some modular forms expansion. And if all of this has happened, and this is doesn't happen generally, then you say that the manifold is weight 2 modular. And so the question is, for which values of the moduli does this occur? Now, this conjecture, due to Caccianelli-Yang, is that at a supersymmetric flux vacuum, the compactifying manifold will be weight 2 modular. So I'm going to now briefly run through just the particular supersymmetric flux vacuum solutions that we look at. There's a few to choose from before showing you some modular forms that can be associated to these. Okay, so before diving into sort of the analysis, let's just remember that a Calabi-Yau threefold has a holomorphic freeform. And if you expand this in some integral symplectic basis, you'll find a vector of period functions. So the components of omega in that basis will be this vector pi that's going to come up a lot. Okay, so you do the usual thing. You put 2b on your Calabi-Yau, and you turn on some fluxes, and you do all this, and you'll acquire a superpotential. Now, what we want to find, where we expect these modular manifolds to be hiding is at the loci and moduli space, where the potential vanishes and the superpotential vanishes. And you take these the equations that define all these things, and you go through this and you work it out, and these are the three equations that you end up wanting to solve. So there's a very nice set of these for hypergeometric models due to de Wolf. Those weren't applicable to us, so we had to sort of look elsewhere. So it can happen very frequently, actually, that for some manifold, if you swap two of the moduli, then two of the components of the period vector are swapped. And I'm going to be saying that a lot, so instead of saying all of that, I'll just call this the property heart. So if you've compactified on a manifold that has that property, then pick these pairs of fluxes, F and H, and constrain the moduli only with a single constraint that you lie on the fixed point of the swapping symmetry. And this will solve nearly all of the equations, bar one. And the one that remains is the equation that defines the axiodilaton. So you solve for the axiodilaton at the end, and you find this, and that's the full solution. And so we began with H21 moduli. We set two of them equal. But in many cases, the value that we've set two of them equal to actually drops out of the rest of the solution. Okay, so I've told you that there's manifolds of this property. We'll have the solution, and we hope to show a modular. And there's a good number of examples that do this. And to get there, I'm going to just briefly talk about complete intersection Calabi-Yaus. These things are very old, but because there's some notation involved, I'll just review what's being said when I show you a symbol like this. So what this means is you look at the vanishing locus in P1 times P3 of one polynomial, and that polynomial's degrees in each of these spaces is 2 and 4. And you can contrast this with this space, which is some subvariety of P3 times P3, given by 3 polynomials with degrees 1, 1, 1, 2, and 2, 1. So I think looking at those two are probably enough to understand what's going on. But more generally, you'd look at some subvariety in a product of projective spaces with a number C of equations with these degrees. And of course, you're probably looking at this and thinking, okay, well, CCs, that's the easiest thing you could have done. There's far more Calabi-Yau manifolds. This is a tiny slice, but this is sort of a minimal working example. We've got it working for these, and with this done, then of course we'll think about the rest of them. Weighted projective spaces as the simplest next example. Okay, so for the manifold defined by this to be a threefold, you should have this equality being true, and most matrices you write down won't be Calabi-Yau. By the adjunction formula, you'll have a Calabi-Yau when you satisfy this equality. Okay, now if we have one of these, there's going to be a second cohomology on this space. And inside that second cohomology will be the pullbacks of the Kähler classes on each of these factors. So there's going to be at least k elements of these of that second cohomology in a basis for that second cohomology. But you could well have more, and I'm going to ignore those cases. So if that's the case, then you say that the manifold is favorable. And the mirrors to those favorable, so I'm now going to just invoke mirror symmetry. The modular manifolds are not going to be these complete intersection manifolds, but they're mirrors. So the mirrors to those will have k complex structure parameters. And if we look at one of these matrices, we could think of swapping two of these factors here, permuting the columns of this, permuting the rows of this matrix. And that would affect some permutation of the complex structure moduli of the mirror. And that's sort of the smoking gun, because if we have a complete intersection Calabi-Yau manifold, and the configuration matrix isn't changed by such a permutation of the rows, then the mirror is going to possess this property heart, so that we get a flux vacuum with supersymmetry, and so then conjecturally that we get modularity. And here are our toys. This is what we're working with. All of these, their mirrors possess this property. Just by way of counterexample, this one doesn't. And we have computed some tables of modular forms for this example, and this last one. And I've put these sort of in, from one end, these are easy to work on because they only have 2 parameters, which makes things quicker. And from the other end, we know that for these cases, there's a very nice paper that I haven't cited here, unfortunately, that's my mistake, by Verrill from 2004, where the periods of these obey a very simple, well, not very simple, recurrence relation that can be used to, you can plug that into our method and shortcut some of the work. And that's also true for this case, and we're getting at these ones in the middle. Okay, so the first example I want to really show you is this one, this bottom right one. So there are 5 complex structure moduli to the mirror, and you can pick any 2 of them and set them equal. So let's just pick the 4th and the 5th. And if you work out what the period functions are and form the axiodilaton as in the solution, then you will find this nice ratio of Bessel moments. And in this case, actually, the dependence on 5,4 was set equal to 5,5, but there is no 5,4 dependence in this axiodilaton. So this whole function can be plugged into the Klein J invariant to get the modulus of what we hope and is the elliptic curve associated to the weight 2 modular forms. And this is sort of what the result looks like. We compute a long table like this on a flux. Sorry, on this table for this particular table, just so it fits on a page, we've set all 3 of these phi1, phi2, phi3 equal to phi. So that done, as you verify, but you didn't have to set those equal to get a solution, you'll find these modular forms, LMFDB labels are given. And then we go on. There's another example. It's exactly the same story. Set the 2 parameters equal. Look at the axiodilaton profile, and you find these. So all of these are new examples that support this this conjecture. And as the last example I can show you, it's just another long table. I neglected to include, the second page of this. Okay. I'd like to give a brief mention to the F-theory uplifts of these flux vacuums. So there we'll find an elliptic fiber with complex structure modulus tau. And in these configurations, that elliptic vibration will be constant over the base. So those J invariants that I showed you earlier, are the J invariants of those F-theory fibers. And if you make a suitable choice of coordinates and you look somewhere in your table of elliptic curves or modular forms, and you make one fix so that to fix the coordinates, then you'll find that across the whole length of the table, the elliptic curves that you find are exactly the one that appears in the F-theory uplift. And that was already the case in the old example, and it continues to be the case in our examples. Okay, and I'll now talk about the last application of our methods. So if you do have a Calabi-Yau threefold and you can show that it's modular, then you can expect that the periods of that manifold will be multiples of the L values associated to those modular forms. And where this is useful is that you could hope that your Calabi-Yau is such that the periods are some useful function. So in the case of the first example I showed you, these periods were Bessel moments. So there's also a some attempt here to understand or to evaluate those as some L values using these correspondences. So in the case of that example, we have these moments, and we can find that there's just 3 examples. There's one of these for each item in the table, where those moments are exactly the L values associated to the given modular forms. And okay, I do apologize, as I realize I've grossly mistimed this talk, but thank you very much for listening.
Thank you. Thank you, Joseph, for the very nice talk. Yes, we have some time for questions. Maybe while people find time for questions, I'll ask one myself. So for future work, what would you think would be more interesting, like to find more applications, or are you trying to go deeper in some application, or maybe trying to find study the conjecture in other examples, or what do you think is interesting? What do you plan to do?
Okay, it's definitely possible to write down more examples and study the conjecture on them, but I think it would be what I'm very motivated to look at is we've got this technique now of studying of computing the zeta function quickly on whichever examples we like, pending improving the code. And the stuff I was talking about at the end, where you can evaluate Calabi-Yau periods as L values. So generally you won't have modularity, but there's some expectation that you have some kind of automorphy. And so there's a hope there then that to pick some general point in the moduli space of your Calabi-Yau manifold, compute the zeta function, and work out some critical values or whatever the appropriate analog is for some automorphic forms, and evaluate the Calabi-Yau periods in terms of those. And if the Calabi-Yau periods are something you care about, like Bessel moments, which will come up in 2D QFT, I think that's a strong use of this method.
Thank you. Are there any other questions?
Hi, I have a few questions. First, thank you for your nice talk. My questions are all more or less related. So whenever you have a zeta function and you're identifying modular forms and all of this, you need to have picked a rational function, a rational model for your Calabi-Yau. So my first question is, from your talk, I infer that your zeta function computations are again going from the PF equations, like happened in the other paper by Philip and Zenia and Van Straten.
Exactly.
How does the choice of PF, how does the PF equation pick out a rational model? I've never understood this.
I'm not sure. I don't have an answer. I've actually, in what I've presented, I've been very coy to avoid rational models. I sort of spoke about the mirrors of these things, and we've computed the zeta function on the mirrors of those without carefully checking.
Okay. Okay. And then my next question, it's basically the same question, but as you know, as you said, we have to cheat and pick the rational model at one point in the elliptic curve family. Do you know, have you guys been able to figure out from having more than one example what information goes into that choice of one rational model? I mean, we did it by taking the modular form we wanted and picking it making sure we got it. Do you guys have a more systematic procedure?
No, we did the same thing you did. We
Okay. And then my third question, sorry to keep asking you a bunch of questions, but
absolutely fine.
So what manifolds exactly can you compute the zeta functions of now? Is it anything of small h21 where you know the PF equations? Are you using some CC specific techniques at this point?
We need the PF equations, and for practicality, we need either to have h21 is 2 or 3. For now, we're hoping to improve that. Or if h21 is 5, you need something like these recurrence relations I spoke about. But it's always, we don't have any examples with a very large h21.
Okay, cool. Thank you.
Thank you. Thank you for the questions.
Okay, is there any other quick question? Okay, if there are no more questions, then we should thank both our speakers again.